Okay, good morning everyone. Good morning. How many of you are here for the first time today? First class? In person? First class, right? Prathambar? For geography. Okay, alright. The others? Any first time? Okay. First class of geography. Okay. Fine. Okay, one question that I had given in the group. Have you all been checking the group size? What language do you all understand properly? Assamese, okay? Baki? English and Assamese. Anybody who does not understand English or Assamese? You don't understand Assamese. You understand English, right? Okay, so primarily we'll communicate in English, and if there's any problem, if there's anything you don't understand, you ask me. Yeah. Achha. ठीक है sir. Okay, so have you been checking the group? Size ka na hai group board? Saisa. Some of you have been answering also, so good. Some of you have not responded at all. So it's basically to help you out. June kora nai. The multiple choice is only to help you out. Tumi invitation poa nai. To tumi koi diba sir. Aji kori diba no. So tar pisot I can you check from the others. Loi roba multiple choice kun gita ase, okay? There's one question that all of you answered wrong about what happens to a star. Ultimately, many of you answered neutron. Okay, neutron is only if, remember how many of you remember the Chandrasekhar limit? What was the Chandrasekhar limit? Correct, okay? If a star's mass is 1.44 times greater than the solar mass, that means the mass of our sun, supernova explosion, right? It explodes, and because of that, either it can collapse into a black hole after the explosion, or it can remain as a smaller star called neutron. Hi, take your seat. So just a quick revision of the star. You all take neutron. It's not neutron. Neutron is only if it explodes, if the mass is greater than the sun. If it does not explode, usually all stars would remain as a white dwarf. Remember that, it remains as a white dwarf. So the right answer was white dwarf. I don't know why you all ticked neutron in the group. Where is that? Yeah, most of you ticked. I think only Sanskriti must have ticked the right answer. The rest, I'm not sure what you all ticked. Right? Okay. So just a quick revision of the solar system. What is nebula? Remember I had told you? Come on.
Cloud of gas and dust.
Very good. Okay, nebula is a cloud of gas and dust. And so they finally believe that it was because it all collapses because of its own gravity, and eventually over time contraction begins to happen. What was the word for contraction? Do you all remember? The word is accretion. Accretion means the dust and the gas particles coming together. Okay, and as they come together, they begin to form quarks, and eventually they begin to form protons, neutrons, electrons. Atoms form hoy. Atoms fuse together. Later they form what? What do they form? What was the primary gas? What we call the fuel? Hydrogen. Okay, and after hydrogen, what is formed? Helium. Okay, so that's just a quick revision. So this is the life of a planet. It starts with accretion. Remember everything, you've seen that, there's this very famous quote, right? We're all dust. Have you seen? We're all dust. It's very popular. Okay, you've not seen. Anyway, so actually, yeah, this is what it believes, that everything started with dust. It was all out of nothing. And then these dust particles eventually over time get together, they solidify, they form structures. Okay, and as more and more of these dust particles come together, they form bigger structures, eventually ending up in the planets that we see today. But it all started with what? Minute particles of dust and gas. So the first stage of a planet after accretion is planetesimals. It's the smallest size. Okay, বুজি পাইছানে? Dust particles বোৰ যেতিয়া একেলগে গোট খোৱা আৰম্ভ হয়, প্ৰথম সাইজটো যোনটো ফৰ্ম হয়, the first size that is formed is what you call a planetesimal. It's the smallest version. You can, I'm calling it a version in your language, okay? So, and then as more and more particles get attracted to it over time, it grows and it forms something called protoplanets. Remember I told you proto means original or the first, okay? So the basic structure of a planet is the protoplanet. And over time, again, more and more particles are coming together because of accretion, okay? Because of the gravitational pull, more particles come together, and what is formed? The bigger planets that you see today. Are you all with me? Are you all sleepy, tired? Okay, so just try to respond so that I at least know you're awake. Otherwise, what's the point? Okay, so then planets are divided into two, depending on their position, okay? It all revolves, we're talking about our solar system. Just a revision, so you've come, Aji Pratham Bar, no? Are you Assamese? I'm just assuming. You're Assamese? Okay. So we're talking about our solar system. How did the solar system evolve? The class before that we did a little about the Big Bang. We did about the evolution of stars. Continuing from there, it's all linked, okay? Now we're talking about solar system. Solar system revolves around what? What's the primary element of our solar system? The sun, right? And all the other planets are revolving around it. So depending on how close or far planets are from the sun, we can divide it into two categories, inner and outer planets. Okay, inner and outer planets. So inner are the ones which are closer to the sun. Remember I told you they are not gaseous in nature, but they have more of the rocky materials. Okay, because they are closer to the sun, so that is one reason why. And the outer planets are further away from the sun, and so they have more. So one thing is that happens is the gas can freeze. Remember I had told you, because they're away from the sun, so obviously temperature is going to be cooler, so the gases can freeze. But because these inner planets are so close to the sun, number one, gravity, number two, solar wind. Okay, remember as the sun has a lot of energy inside. Today we'll be doing in details about the sun, and that energy goes out as light. It can also go out, you can also feel it eventually as solar wind. And that solar wind causes the gas which is around the inner planets, it pushes it away. Which is, it's like a force. Okay, the solar wind pushes the gases around the inner planets further away. And so all that is left behind is the rocky, crusty material. But for the planets which are further away from the sun, A, temperature is cooler, so definitely the gas can freeze. And number two, because solar wind impact is not much, they can still hold the lighter gases. Okay, is that okay? So just remember, inner planet hole, it will be hard, rocky, crusty. If it's the outer planets, that means further away from the sun, they are more gaseous. Okay, and always, this is the basic thing, always the heavier elements will sink to the core and the lighter elements, because of the lower density, would move further outside towards the surface. Okay, this is how the solar system looks. What was the shortcut I told you? Who remembers? Shortcut to ki asile? Ye kiska pen hai? Tick. Alright. What is the shortcut? Yeah, my very. To remember the position of the planets. Yeah? Yeah? Go on. Oh, okay. What else just happened? Oh, can't do this. कहाँ पे ये? Left. Yeah. This. Okay. Oh yeah. Thank you. Okay, here. My very elegant mother just showed us 9, and when Pluto still was considered a planet, so P used to be here, but now this has become a dwarf planet, so ye nahi hai. So this sentence doesn't make complete sense now, but it'll still help you. Okay, if you're going to remember which planet is closer to the sun, just remember this. My very elegant mother just showed us 9 planets. So we start with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, so this is one easy way for you to remember which are the inner planets and which are the outer planets. Okay. How do I do this? ये क्यों नहीं हिल रहा अभी? What am I supposed to do to this? Okay. Spherical Earth, that the Earth is round. Pythagoras, Aristotle, these are the guys who figured it out. Before that, it was believed that the Earth is flat. Okay, they did not believe that the Earth is round. How did they figure out that the Earth is round? Remember, I told you during an were you all sleeping? Huh? During a lunar eclipse, the shadow of the Earth was seen, and that's when they saw that it was curved. And so they figured out that the Earth is not flat, it definitely has to be round. Okay. And then we have the Kepler's law, which we have already done. Okay, the orbit of the the planet is an ellipse with the sun at one foot of the 2 foci. I had explained to you, foci is what? There is the major axis, right? Okay. I have to do this annotation or this. Oh yeah, this. Why do I keep forgetting? Yeah. Okay. So I had told you, suppose this is a planet and this is the sun, right? So imagine there is an imaginary line. We call this the major axis. And if I'm going to divide this into 2, then one part of it is the semi-major axis. Half of the entire axis is considered to be the semi-major axis. So it is believed. Okay, abhi ye kahan chala gaya? Yeah. So the planet is here. Okay, I'm going to draw an imaginary line. Okay, so suppose from the center, the 2 equal sides. These 2 sides are called the foci. So in one side of the foci is the sun. That is what this Kepler's first law states. Okay. And then after that, a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. So basically, if a planet is moving from position A to position B in a particular period of time, position 3 to position 4 in a particular period of time, if the time taken is the same, they have covered equal area. That means within the equal span of time, they are covering equal area. A planet will always cover equal area when it is revolving around the sun. Do you understand that? The second Kepler's law. And the third one basically states that the further away you go from the sun, the more time you're going to take to revolve around it. Basic, right? If the semi-major axis here, the square of the orbital period of a planet is proportional to the cube of a semi-major axis of its orbit. So the time taken will be doubled if the semi-major axis, that means half of the axis has been tripled. Okay, so basically the further you go from the sun, Jiman due to be sun or pragotakiba at a planet or position, hey planet to a sun or akebake ghuribole himane besi time lobo. That's what Kepler's third law states. Okay. Fine. Again. So these are a few facts. Okay, surface temperature of each of the planets, period of rotation. There's nothing to explain over here. You have to memorize this. Do you get these PPTs? Did anybody receive these PPTs? No, right? But in the video, when you rewatch it, this will be there. You can always take screenshots, and I'll send some of them as PDF in your group. So you can take, but try and write notes now. Okay, if you write, you'll remember. That's why I'm encouraging you to write. Just listening, you'll forget everything. So write as much as you can. Write, you'll remember. So these are some of the basic facts. How much time you take to rotate. Rotate means around a planet's own axis. How much time it takes. That's called rotation. And how much time it's taking to go around the sun. That's called revolution. Okay? Then distance in astronomical unit, diameter, size. Okay. Here the largest planet is which one? Jupiter is the largest planet. Smallest is Mercury. Okay. Then you have how many moons do they have? Also, you've seen here. This is very common. Which planet has the highest number of moons? Saturn has the highest number of moons. And density is also given, and specific gravity. Hi, Rita. 149. Saturn May. That's updated. Okay, I'll check that. Okay. So this is it, the basic position of each planet in comparison to the sun. Okay. These are the dwarf planets here, the smaller planets. Distance traveled by light in 1 year. It is not the time, but it actually shows the distance. Even though we say light, distance covered, okay, by light in a year. So don't get confused with that. Time and formation. Planets formed about 4.6 billion years ago. Solar nebula collapse, core formation. Okay, same thing repeated. Very similar. It's all similar to. It comes from the Big Bang. Okay, it all originated from there. And if you know how stars evolved, if you remember that, it goes around the same sequence. It's not very different. Okay, this is a little about the moon. Okay, these are some facts you can go through how the moon affects the Earth. So basically, the moon has its own gravity, and the gravitational pull from the moon, it actually pulls the tides, okay, the water in the surface of the Earth. And so depending on the direction of the moon, the tides also begin to wherever the moon is located, you will see the gravitational pull has an effect on the tides. So it creates high tides and low tides. The rise and fall of tides, Earth's rotation. These are not required so much in details. If I'm going to go to this, they're very, very complex. If I'm going to explain in details how the moon affects the Earth. So let's just remember these 3 points. Friction between the tides and the Earth gradually slows down a planet's rotation. And moon's distance, as the Earth slows, the moon moves slightly further away each year. This inner planets and outer planets. And remember, the outer planets are always bigger. Okay, they're larger in size as compared to the inner planets. So inner planets are closer to the sun before the asteroid belt. Composition is rocky and metallic with high densities. They are mostly solid. The gas, remember I told you solar winds push away the gas, and apart from that, because it's too hot, so it's not going to, you don't get, the gases don't get a chance to freeze. Okay, so they're pushed. So that's why the inner planets, they are all rocky. Remember that they are more gaseous in nature, so they're also called gas giants. These are called what? Gas giants. Most planets rotate clockwise, like rotation, retrograde, and Uranus clockwise, retrograde. Yeah, this is important. Inner planets and outer planets, also known as terrestrial. Remember I told you terrestrial means anything to do with land. You've heard this since the time you're kids, right? Terrestrial animals, aquatic animals. Terrestrial means land. So it's all rocky, crusty, but Mercury, Venus, Earth, Mars. Nearer to the sun, move faster and have a shorter period of revolution. This is again Kepler's third law. Because these are nearer to the sun, they are taking shorter time for revolution. Okay. Thin and rocky crust and mantle is rich in iron and magnesium, have solid surface, no ring systems around them, thin atmosphere. Ring system, the ring is basically nothing but gas and dust. Okay, that because of the gravity. But obviously, because they're close to the sun, the gas and the dust cannot stay. The solar winds push it, because these are light elements, you understand? Because it's dense, the density is very less. So they are very light. They can easily be pushed by solar winds. And so there's no ring around these inner planets. Because I'm telling you, the ring is not a solid matter. The ring is actually just, it's dust and gas. Okay, but in these inner planets, there's no ring. Why? Because there's no opportunity for the dust and the gas to form a ring. It's pushed away. All the lighter elements, the solar winds push it back. Okay. No ring system around them, thin atmosphere, very less number or no natural satellite. Then these are outer planets, also known as Jovian planets. So they may not use the word outer planet. They may say what are Jovian planets. You have to remember, Jovian is the same as outer planets. Okay, Jupiter, Saturn, Uranus and Neptune, far away from the sun, move slowly. Again, Kepler's law, further away, so more revolution time. These are the gaseous bodies, and mantle is also made of gas, do not have solid surface. Rings are present around these planets. Why? Because the impact of solar wind is less. So because of the gravity, the dust and gas is able to form a ring. Okay. Large number of natural satellites. This is important. Remember this. Large number of natural satellites. But in case of the inner planets, either there are lesser satellites, or in some planets, no satellites at all. Okay. Here. Reason for inner rocky planets, proximity to the sun. It's too hot for gases to freeze into solid. I already explained that to you. Okay, obviously if something is hot, it cannot freeze. So the gases don't get an opportunity to freeze. So instead what happens? It's solar wind. Remember, the closer you are to the sun is we'll be doing in details today about the sun. So there is something called solar wind. Okay, it's basically a certain amount of energy that the sun releases in the outer sphere of the sun. So because of that wind, what happens is all the lighter gases are pushed off. Okay, and so there's no gas around the inner planets, and then there's weak gravity. Smaller size of inner planets means weak gravity, making it harder to hold on to lighter gases. The exact opposite is gaseous outer planets. It's cold enough, so gases freeze, weaker solar wind, so they are able to retain the gas. This we've already discussed. Okay, do you remember? Which of the following conditions is most relevant for the presence of life on Mars? Correct, okay, because I'll remove this one. Okay. Yeah, occurrence of ice. And then you have this one. We'd already done this, but I told you something was wrong with this. The codes given here, one is incorrect. The right code is not given over here. But anyway, you tell me which is the smallest planet? Jupiter. Planet second from the sun in the smallest solar system? Venus. And planet nearest to the sun? Mercury again. Okay, so the code here is wrong. Earth does not fit any of the options. Among the following, which planet takes maximum time? Yeah, Jupiter, correct. In order of their distances, why does it take maximum time? Furthest away from the sun. In order of their distances from the sun, which of the following planets lies between Mars and Uranus? Jupiter and Saturn. For those in the last class, you already remember the answers. Which one of the following planets has largest number of natural satellites or moons? Saturn. Okay. Let me do this. Okay, today we are going to do in details about the sun, because of which we're all alive in a huge way. Without this, climate on the earth is not going to be habitable. You understand when I say habitable? What does it mean when I say habitable? Suitable for living. Okay, so this is the sun, and this is what makes the earth to a huge extent suitable for living. What is the sun? What is it? Okay, that's always going to be the right answer. It's a very clever answer. It's never going to be wrong. But in general, how would you describe the sun? What is it? What do you understand it to be?
Star.
Correct, okay? The sun is a star. Like all the other stars that we have in our galaxy, the sun is one of them. But why does it look so different, so big? Does not look like the stars you see at night. Correct, okay? Basic common sense. The sun is much nearer to us as compared to the other stars, but that's not all, okay? The sun in itself is a very big star. Compared to the other stars that you see in the galaxy, the size of this particular star is very big. It's not just that it's small, but because it's close, it appears big. No, it's very big. In fact, it would rank among the top 10%. If I'm going to look at all the stars of our galaxy, this particular star, the sun, our solar system sun, it comes in the top 10% of stars in our galaxy, size-wise. Okay, so it's very huge. What else? Let me just give you a few facts. The sun is actually so big that it can accommodate 1 million Earths inside it. Can you imagine how huge it must be? How big is our planet, right? And 1 million Earths can actually go inside the sun. So just wrote a few facts. Big hot ball, blah blah blah. Okay. Yeah. Okay, again, how is the sun formed? We come back to the same idea of a nebula. It all starts with nebula. That's why I told you they say we're all dust. It all starts with dust and gas. But we'll go in details. I'll show you eventually. The sun is very different from other stars. It's not just dust and gas. Something else is there inside which makes it so hot, which makes it so bright that you can't look at it with your naked eye. Okay, so we're going to get into details of that, but first thing here is it's a giant gas because of gravity, and it must have been triggered. What triggers this collapse? Maybe some other stuff. These are all hypotheses, okay? You understand hypothesis? It's an assumption. A lot of what we are studying now is assumptions, and like I've told you in previous classes, many fill in the blanks are there, which science will hopefully be able to understand or answer in the coming years. So even here, what causes this collapse of this particular nebula? One guess is that maybe a star nearby explodes. And so energy is released from that supernova. That has an impact on this other nebula and it collapses. Okay, do you understand what I'm saying? The sun has been there existing as a nebula. Some other star, maybe around the sun, has finished its lifespan and there's the supernova explosion of that star. Obviously, when a star explodes, what is released? Heat, energy, right? It'll have an impact on what's happening around. You can imagine like a nuclear explosion. It'll have an impact around, right? So it's assumed that maybe that supernova explosion has an impact on the sun's nebula and eventually causes it to collapse. Okay? The dust and the gas particles, and eventually getting denser, hotter, and eventually becoming again original. Okay, the first of its form, the proton, or it's also called a pre-star. Then nuclear fusion takes place. What is required for fusion to take place? Temperature. Very high temperature is required in order for fusion. What is fusion? What is nuclear fusion? हाँ पता है. It's okay, sit. First class today. So please tell me what is fusion? Nuclear fusion, we've done it. Just इतना detail में जाने की ज़रूरत नहीं है, but basics. What do you understand nuclear fusion? Coming together of No, you're talking about hydrogen fusion. So they're coming together of two nuclei. Okay, when they come together and they form with a nucleus. So that is what you understand by nuclear fusion. So the core, what do you understand by, when I say core, right? You can consider it to be like the heart. Okay, so when I say core of the sun, it's like the heart of the sun. Okay, and so the core of the sun is extremely hot. And what is happening inside that? What is there? Hydrogen. And because of the hot temperature, right, what's happening? Fusion is taking place. But the fusion of this hydrogen inside the core of the sun, the heart of the sun, is very different. Why? Because the temperature is extreme. And so something unique happens because of this extreme temperature. Do you know what happens? Ions are formed. Do you know what are ions? You've heard of iron, right? What is iron? Charged particles, correct. So now they have positive and negative charge. Because of the hot temperature inside, these atoms begin to get charged, and what happens, you know, the electrons get separated. The electrons become independent electrons. They come out of the atom. From the basic structure, from the single parent atom, these electrons come out. And what is left behind? The proton. And so ultimately it is the protons that fuse together and form helium. And the electrons, you'll see what happens. The electrons are left outside as floating electrons. And wo jo hota hai na andar, the charged liquid, you can consider it to be like the charged, not liquid, it's gas. Okay. So this charged gas inside the sun is what you call plasma. So I'm just telling you what's there in the core. So this is where it's a little, I'm going into a little more detail. Okay, I have a khali page over here. So I'm considering this to be the core of the sun. So I'm telling you, this is the heart, where everything originates from here. Okay, the sun that you see, the light, the heat, everything starts here. So what happens inside this? Extreme temperature, right? And so there are these particles that are there inside. Proton, it all starts with quarks, the usual, okay? But because of the extreme heat, what happens is these atoms begin to split. They get charged, okay? And so what happens is now there are protons and you have electrons. Protons and electrons are there. The electrons get separated out. And all that's left behind now inside is also protons. Together, a fusion, and this forms your hydrogen and eventually forms helium, heavier elements. Electrons, in case of the sun, remain floating. Okay? Protoplanetary disk. Okay, this is the basics. The dust, the heat begins to come in together. Accretion hota hai. They begin to contract, they come together, forming these basic structures. Gas is left. Okay, and what is left behind forms this protoplanetary disk-like structure, orbits around the sun, forming a flat disk. Okay, I'll get into this. So just remember, what have I done? Yeah. So just remember, inside the sun, what's unique? It has plasma. What is plasma? Charged particles. Okay, that's what's different about the sun. And this has a huge impact later on what's happening outside. क्यों नहीं जा रहा है? Some facts about the sun: 4.6 billion years old, temperature is about 6,000 degrees Celsius on the surface, 16 million degrees Celsius in the core. Can you imagine that? It's about what, 35 degrees today. Okay, so the core of the sun is 16 million degrees Celsius. It's extremely unimaginably hot. And obviously as you go to the surface, it's a little cooler. So it's 6,000 degrees Celsius. Density is 1.41 times that of water. And Earth's overall density is 5.5 times that of water. Okay. The surface gravity of the sun is 274. Comparatively, the surface gravity. Okay, these are just facts. Do you want me to get into the details of this? Just take a picture or do something. Yeah, take a picture of this. And you just have to memorize. Okay, so I'm not going to get into all this. There's more that I need to go into. I'll just be wasting time if I'm getting into this. This is important. Composition, 98% of it is hydrogen and helium. The remaining 2% would be your dust. Dust. Okay, it's all gas and dust. And how long does it take to rotate? 25 days and 9 hours.
What is counterclockwise?
Counterclockwise matlab not the anti-clockwise. Counter matlab ulta, the opposite. Okay? Ha. Okay, so counterclockwise means the other way around. Clockwise, you understand, it's going this way. Anti-clockwise is counter matlab anti-clockwise. Okay? When viewed from along above the Earth's north pole. Okay. Angular momentum. Okay, this is all done. I'm coming to this now. This is what is important for all of you. So this is the inner layer of the sun, which has your hydrogen fusion happening inside. And remember, I told you what happens. The electrons are left as independent. They have split out of the atom. So the only thing now what is fusing is protons. The protons are fusing together. Hydrogen ban gaya hai helium. Now can you tell me what happens when something becomes hot? What begins to happen? Because it's hot here now. The gases are hot. What's going to happen next? What happens to hot gas? It expands. When something expands, what happens? Its density decreases. And if its density decreases, what's going to happen? Imagine a hot air balloon. The minute you light the fire, हाँ light हो जाता है. उसके बाद क्या होता है? उसके बाद उड़ने लगता है, right? So hot air basically rises up. So that's exactly what happens with the sun. Core में what do you have? You have the hot air, right? You have the helium, which basically you have plasma. Just consider it to be plasma. And the plasma is basically your hot gases, which are also charged. Now, if something is charged, okay, when charged particles begin to move, what happens? What does it have? What do charged particles have? I mean, it's too much of physics, so much is not required, but I want you to understand the base of it, okay?
Charged particles का movements in the current.
Uh-huh. Current, not exactly current. Okay, that's one part of it. That's important. The magnetic field. What do you understand by magnetic field? Simply put, it's an invisible force around. Okay, that has an impact on the objects around it, like a magnet. Imagine like a chumbak. It has a magnetic field. Okay, because it's charged, right? So what happens around it? It's able to exert a force. It's an invisible force. That's exactly what happens with the gases inside of the core. I told you क्या हुआ है अंदर में, because it's hot, right? The electrons split and the protons are also there. They are charged now. Inside it's charged. So not that it's just hot, but hot होने के साथ साथ it also now has a magnetic field. Now because of convection, you know what is convection? Convection is this, transfer of heat, right? Hot air rising up, cool air rising down. So convection also happens. Please tell me if you lose me somewhere, okay? Any point that you don't understand, that doesn't make sense, please ask me. So what happens is there is hot air inside here, okay? And because of its density reducing, because it's hot, it has expanded, right? And so now its density has reduced, it's become lighter. Light होने से क्या होगा? It's going to go out. So that's how the gases, okay, begin to be pushed out. But along with that, what's happening? Fusion will keep happening, because of which light is also going to go out. Energy, see, when hydrogen atoms are going to be coming together through nuclear fusion and forming helium, a certain portion of it, I'll give you the exact, I have written it down. हाँ, energy release होता है, which you will see in the form of light. Okay, how much happens per second? I had written that down actually. Per second of a day. मैंने कहाँ लिख दिया? Now I am so clever. I don't remember where I wrote it. Yeah. So every second of every day, sun converts every second. Okay, imagine that. 700 million tons of hydrogen is converted into 695 million tons of helium. That happens every second. 700 million tons of hydrogen, nuclear fusion happens, and 695 million tons of helium is formed. So how much have you lost? Certain amount gets lost. 5 million tons. You're getting the math? 700, if I have 700 million tons of hydrogen, I'm going to be converting this now into helium. I originally took how much? 700. But helium, how much am I getting? 695. So there's a loss, right? I lost 5 million tons. That 5 million tons that you lose is actually what is exerted out as light energy. That's the light that you ultimately see in your sun. That's enough. That 5 million tons per second of every day that is released by the sun is enough to keep the sun alive. Okay? That's way too much details, I think. But just an interesting fact. I found it interesting. I don't know if you all find it boring, but okay, so this is what happens here. The core, uske baad what happens is, the next layer outside of that is what you call the radioactive zone. Nothing much. What is happening here is the plasma is pushing out, being pushed out, along with the magnetic field. Remember I told you because of what? Convection. Because now it's hot, it's less dense, so it's being pushed out. Okay, and then ultimately it reaches the outer layer of, it's the third layer of the inner layer actually, you call it the convection zone. From the name itself you understand convection is happening over here. Okay, so what happens? The plasma and the electromagnetic field along with the plasma. Because why do they have magnetic field? Because they are all charged. And whenever something is charged, just remember, if it's charged and in motion, it will create a magnetic field. What causes this motion to happen? Why do you think the plasma moves? Number one is convection. I told you obviously because of density. Second reason is because of the solar rotation. The sun is rotating on its own axis also. You understand? It's moving. So that also causes the plasma to be pushed up. These are the two factors. So ultimately, plasma, which is your charged particles, along with the magnetic field, because of convection, the first reason is what? Convection. And number two is your solar. These are the two reasons, okay, why the plasma which is inside is being pushed out now gradually. And it can take up to 1 million years for this entire process to be completed. You know, it's actually believed that the sunlight that you see today, whatever you see, it actually, the process of that light reaching on the outside surface started about 200,000 years back. And dhire dhire when the plasma begins to go out, okay, because of convection and solar rotation, it takes about 200,000 years. And then finally the light you see on the outside. And what is that light? Because I told you that 5 million tons that it loses every time when fusion happens, right? Hydrogen se helium banne mein thoda energy loss ho jata hai. And that energy loss comes out in the form of light. Okay, that is every second, by the way. I'm just telling you about every second. So convection and solar rotation results in this plasma being pushed now to the convection zone. And then again, the next layer after the convection zone is the photosphere. These are now the outer layers. You can consider this to be the sun's atmosphere. So like we have our own layers, right, of the atmosphere. You have atmosphere, you have stratosphere, you have troposphere. The earth has an atmosphere, right? The sun also has an atmosphere. And these are the layers of the sun's atmosphere. Photosphere, chromosphere, then there's a transition region in between, and you have the corona, which is the outermost layer of the sun. Just remember this, outermost layer of the sun, corona. Now remember, I'll come a little to this now. What are sunspots? Is it clear till here? Can you explain to me now if I ask you? Just explain a little to me. What have you understood so far? What happens from the core? What's there inside the core? It's really hot. We know that. Okay, and so there are the quarks are there, but because of the heat, eventually what happens? These particles begin to get charged. And what happens? The electrons they are removed or separated, you can say, from the parent atom. You understand an atom, right? So an atom has, within the atom there are structures. You have the electrons, you have the proton, and you have the neutron, right? So once the electron has moved out, what is left behind is the proton, which will fuse with another proton, and these are what will form your gases ultimately. So hydrogen banta hai, uske baad when hydrogen atoms begin to fuse together through nuclear fusion, what happens is helium is eventually formed, a heavier element is formed. But because these elements inside the core are charged, what is there? What do they also have? You only give the answer. Kya tha? Because they are charged. Magnetic field. They all have, just remember, each of them will have a magnetic field. And what is this charged interior called? I told you. Inside the core here, ye jo charged interior hai, what is this called? Inside the core. It's like a charged soup of gases.
Plasma.
Yes, correct. Okay, this is the plasma, which is inside the core. Now, eventually what happens with this plasma, so both of them are like working together. You can imagine these two friends, plasma and magnetic field, they are together now. Okay, and they're on their way out. They're going out now from the core. They're beginning to move out now to the outer layers of the sun. What is helping them to move out? What is helping these two friends, plasma and electromagnetic field, to move out from the core? Convection and solar rotation. Okay, so what do you how is convection helping? How is convection helping? बोल दो, कोई बात नहीं, गलती होने से भी बोल दो. एग्जाम में गलती होने से यही गलती होना बेहतर है, so just say it. Okay, so basic element, just remember the hot air balloon. When you're saying convection, no, forget everything else, just remember hot air balloon. Hot air will always rise up. Why? Because it is expanding. The minute you heat something up, just remember water, take an ice cube, you heat up an ice cube, what's going to happen? It's going to expand, right? It melts. And what's happening? As it melts first, the density is reducing from the solid state to the liquid state. And finally, when the density has gone really low, because it's expanded, right? The molecules, the atoms inside have expanded. What's happening? It's going to become so light that it will vaporize. The density will become much lower than the density of the air around, and it will rise up. You all look at me like I'm teaching alien stuff. Is it making sense? Is it making sense? Just remember, it's hot, it's light, it's going to go up. You forget everything else, remember the ice cube. What will happen if you heat up the ice cube? Eventually it's going to vaporize, nothing is left behind because it's become less dense. It's become extremely light. Okay, the density. You understand density, right? What is density? What about the rest of you? Just basics mein bol do, isko to he knows properly. What about the rest of you? Density is basically how packed is something. Okay, how packed are the molecules of a particular object. So if it's this way, if it's packed this way, what is it? Extremely dense, right? Then when I'm going to put in heat over here, what's going to happen? Gradually the molecules are going to, there's going to be some space, right? It's going to expand. And eventually if I'm going to put more heat over here, it's going to expand completely. And it's going to become so light, it's going to become lighter than the density of the air, and it's going to rise up. So that's exactly what happens with the plasma here. So hot. If it's going to be so hot, imagine I'm going to keep putting in more heat. Okay, fusion ho raha hai. Fusion hone se heat is also going to be, both are simultaneous, right? Energy is being released. It's extremely hot at the core. And because it's so hot at the core, what is happening? The plasma and the magnetic field. Don't forget this. If you forget magnetic field, then all of this, we are not going to be able to reach flare, uske baad sunspot, all of this, we will not reach all this if you take out magnetic field. सिर्फ plasma नहीं उठता है. Plasma के साथ और एक चीज़ होता है. I told you they are two friends. You cannot separate these friends. Who are they? Electromagnetic field and plasma. हाथ पकड़ के दोनों साथ में ऊपर उठ रहे हैं अभी. And what is helping them go out from the core? Convection and solar rotation, right? So now gradually they begin to move out, and what happens? As it's beginning to move out, right? It's moving away from the core. The core is the hottest part. The further you move from the core, will it be hot or cold? Correct, right? Naturally. Core, I told you, is the hottest part of the sun. It's like the heart. Okay, जहाँ से शुरुआत हुई है, that's the core, and that's the hottest part. If I'm going to move away from it, what's going to happen? It's going to get colder, right? So धीरे धीरे क्या होता है? ये plasma जो है, this plasma and the electromagnetic field are moving to the outer layers. So they are moving away from the core. Because they are moving away from the core, बाहर जा रहे हैं अभी core से. क्यों? Convection की वजह से और solar rotation की वजह से. They are moving out from the core layer. What's going to happen now? The plasma is going to cool down. Naturally, over time, क्योंकि core से temperature नहीं मिल रहा अभी. It's moving further away. So the plasma is going to cool down. And so what happens if something cools down? If hot air rises, cool air, क्या होता है? Cool air को क्या होता है? It settles down, obviously. Hot होने से you're going up, cool होने से you're coming down. So this plasma, when it's gone out now, it's cooling down. And so usually what happens is, it's because its temperature drops, its density increases. फिर दोबारा से यहाँ पे था, अभी temperature कम होके यहाँ जा रहा है, फिर original structure में वापस आने वाला है. Okay, it's going to come back to the heavier elements. And so what's going to happen? Density बढ़ गया because it's cooling down. And so usually it all drops back to the core. And ये चलते रहता है. But sometimes something unique happens. Okay, something unique happens. These electromagnetic fields, you can consider them to be like springs. Okay, just imagine them to be like a spring. So these electromagnetic fields, they are like lines. Okay, and what happens is sometimes they don't allow, they prevent. Why they prevent, we don't know. But sometimes, in some cases, they prevent the plasma from being dropped down. Okay, and so instead of being dropped down, the plasma remains on the outside का जो region है, corona में, the outermost layer में plasma रह जाता है. And it begins to cool over there. Remember, plasma will have light so long as it has heat. Fusion होते ही रहने तक ही it's going to have light. When the fusion has stopped, okay, why will it stop? Because heat is reduced. When you come to the outer layer, right, corona में पहुंचने के बाद what's happened? It's become cool because I'm far away from the. But there's another very strange thing. Corona, however, is much hotter than the inner layers. Why? This is one question that science is still trying to figure out. Surface temperature ज़्यादा रहता है. But if you go as per the basic logic, further you move from the core, it's supposed to be cooler. But corona is actually much hotter. Not as hot as the core, obviously, but it's hotter than these inner layers. Okay, so remember the plasma, imagine the plasma now has reached the corona. And usually what should happen? It's cooled down. The plasma is cooling down. Density is increasing. So usually it should sink back to the core. Okay, it begins to again, वो पूरा cycle दोबारा repeat होके, it's going to come back to the core. It's like घर से बाहर गया था, फिर अभी now it's going to come back home. But in some cases, something unique happens, but the electromagnetic fields of the plasma, I told you they're like these, imagine there's this invisible force, they don't allow the plasma to fall back to the core. So plasma corona में ही रह जाता है. but it doesn't have enough heat to have fusion also. So क्या होता है, वहीं पे it begins to cool, and if it's cooling down, it has no light, and so it forms these dark spots on the sun. So can you see here? So we call these sunspots. So when the plasma cools down, and it cools down on the corona, on the outer surface of the sun, they form these dark spots called sunspots. And these sunspots are so huge, usually you can see them with your naked eye. If you are, that's why if you look at the sun properly, it's not even. It actually has dark spots in it, but we usually can't see it. Why can't we see it? I'll explain that to you. So technically, if the corona is there, which is the outer layer of the sun, right? And all the plasma has settled. Suppose there's been a huge amount of plasma which has cooled down on the outer surface, and it's become a dark spot. It has become a sunspot. This sunspot should actually prevent light from going out. So what is it that, how do you think we get the light then? Because the sun has a lot of sunspots, which are these black dark spots, and still the sun emits so much light. How do you think that happens? Let me just see if I missed out anything. फ्यूजन नहीं हो रहा अभी बाहर में आके, अभी तो प्लाज्मा इज कूल डाउन and it's settled, suppose as अंदर में हो रहा है in the core, okay, it's hot, fusion is happening, ठीक है, a certain amount of light is there, but light के साथ साथ sunspots भी बन रहे हैं. तो why do you think, how is the sun still able to emit so much light? Okay, I'll tell you. Suppose there is a, can you see here? Suppose this is a sunspot, okay? Okay, can you see here? These are sunspots. Basically cool down plasma that the electromagnetic fields didn't allow to go back to the core. Understood? So the plasma is cooled down over here, and obviously no heat, no light, so they settle down on the surface as sunspots. But something unique happens, okay? Around each of these sunspots, there is still a magnetic field. Obviously, because plasma, it went out as charge, right? So the magnetic field around the edge of each sunspot, for some odd reason, they begin to become really strong. हर एक sunspot के edge में, the magnetic field becomes really strong, and it attracts a certain amount of plasma, रह जाता है. And it still continues to get charged because of the magnetic field that's around. It still exists. Not all of it cools down at the same time, right? एक साथ पूरी तरह से plasma will not all of it will sink, not all of it will settle. Some amount of it still remains around sunspots, the plasma, okay? And what happens, because of the magnetic field, they are extremely charged, and like you said, fusion only on the edges of the sunspots में fusion होते रहता है, and they form a certain amount of light which you call faculae. Write it here. Faculae, which means little torch. All of this is happening on the edge of a sunspot. Sunspot के edge में magnetic field becomes very strong, and certain amount of plasma is still there. And what's happening? Fusion is still happening, only in the edge of a sunspot. And उसके वजह से light is released, which is called faculae. Faculae, or little torch, and the light that is released in the faculae is actually enough to make the sun shine. So even though there are these sunspots, it's the faculae that helps the sun to keep shining. जो sunspots के surrounding में जो light is released, that is more than enough to keep giving the sun light. So that's what helps us to get light. Faculae. So remember, plasma, all of it, same thing does not happen to the entire plasma. Certain amount of it cools down and comes back in. Certain portion of that plasma that has gone up will remain as a sunspot. But usse bhi sunspot ke edge mein certain amount may still be active, okay, and still may be emitting light, which is the faculae. Okay, and that faculae is what will give the sun its light, despite the dark spots. It's the dark spots versus faculae. Faculae is stronger, and so it helps to be able to give us light. Okay, remember, corona is the outermost layer, core is the innermost layer. Here, energy created in the core moves outward through radioactive zone and then the convection zone. Okay, so remember, core or convection zone ke beech mein what is there? The intermediary zone, the middle zone is radioactive zone. Okay, and the temperature gradient, the temperature gets cooler as you move from the core. Okay, just a revision. Tell me if you don't understand anything. Internal structure and atmosphere of the sun. Core is the heart. When nuclear fusion occurs, hydrogen fuses into helium, releasing immense energy. It's the hottest part of the sun, the core. Radiative zone, energy travels towards as electromagnetic radiation. I told you this. यहाँ पे direct electromagnetic radiation है, but I've told you why is there an electromagnetic radiation? Because inside the core, what's happening? The electrons are splitting out of the atom because of extreme temperature, and so there are these independent floating electrons. And remember, basic principle: whenever charged particles are in motion, they will have a magnetic field. What is magnetic field? Invisible force around them. Okay. So this process is slower than in convection zone. Convection zone is the outermost layer of the sun's interior. Energy moves via rising and falling currents of hot gas like boiling water. I've already given you that example. Cooler than the layers below, allowing heavier elements to hold onto some electrons. Then you have the photosphere. This is the visible surface of the sun. Appearance is bright and uneven. Around 6,000 degrees at the outer edge, emits most of the sunlight that we see, the photosphere. Chromosphere lies above the photosphere. Difficult to see normally, visible as a reddish ring during a solar eclipse. Surprisingly, it gets hotter as you move away from the sun's core, the chromosphere. Then here, sunspots, dark cool patches on the sun's surface caused by strong magnetic fields that block some of the sun's heat and light. So basically, sun's heat and light, it's the plasma. The magnetic field, when it does not allow the plasma to sink back into the core, some of the plasma cools on the sun's surface, forming sunspots, okay, which are these dark patches. So a sunspot has a dark center and a lighter surrounding area. So the dark center is what you call the umbra, and the lighter surrounding area is the penumbra. Just remember this, just write this down. Sunspot. The dark center is the umbra, the lighter surrounding area is the penumbra. The sunspots may be temporary, okay, they may just last for a short span of time. They can last from days to months. More the sunspots means the sun is more active. Obviously, that means more quickly is there more plasma coming out to the surface and more electromagnetic field, which is not allowing a plasma to go in back to the core. So the sun is definitely more active if there are more sunspots. When there are few or no sunspots, the sun might become slightly cooler. This could have minor effects on the Earth's climate, but is not the primary driver of long-term climate change. Okay. What's wrong with this? This is corona, the outermost layer of the sun's atmosphere located above the chromosphere. Visibility, it appears as glowing white halo during a total solar eclipse. Okay, anything? Kiba, any doubt? No? Solar flares, sudden bursts of energy from the sun's surface due to magnetic disturbance. Okay, I told you, imagine the magnetic fields to be like spring. Okay, just for your imagination. Obviously, you can't see them that way, but imagine them to be like spring. When I'm holding a spring this way, right, there's a lot of what? What does it have inside it? A lot of stored energy, right? What you call potential energy. The minute I release it, what happens? The energy is released. Sometimes what happens is these magnetic fields, which are like springs, they tend to intertwine with one another, they break, they join. A lot can happen to these magnetic fields. Sometimes if they break, okay, there is a certain amount of force exerted, okay, and they result in something called a sun flare, like a sun burst. And certain material from the sun is exploded. You understand? This happens because of the impact of the magnetic field. And it's usually very strong. I think it happened a few years ago, if I'm not mistaken. And if this were to actually happen, it can cause, if a really strong sun flare happens, it can cause a worldwide blackout. Okay, we can actually lose electricity, we can lose light. Sudden bursts of energy from the sun's surface due to magnetic disturbance. Okay, not much, you don't have to understand much in detail, but just the magnetic fields sometimes, like I said, they can intertwine, they can break. Okay, and because of magnetic disturbances, there are these explosions that happen in certain portions of the sun, and certain material from the sun. Obviously, if there's an explosion, certain material, some amount of dust, some amount of gas is also going to be lost. So they appear as bright flashes of light, incredibly hot, reaching temperatures 10 and 20 million degrees Celsius. Okay. Solar wind, a stream of extremely hot charged particles flowing out of the sun. It travels at incredibly high speed. Okay, so when these charged particles are moving, right? Remember I told you plasma, electron, protons are there. These charged particles, when they are moving out from the sun, they release certain amount of energy, which is felt in the form of wind. You'd feel it like wind. Okay, so you call that solar wind. And it travels at an incredibly high speed, 900 kilometers per second. It's unbelievable. Key points, made of plasma. This means the atoms in the solar wind are superheated, causing them to split into charged particles. The sun's outer atmosphere, okay, it all origins from the sun's outer atmosphere, called corona. Obviously, because I told you, in the corona, certain amount of plasma is still left, right? And so as these protons and electrons, they keep moving, they release energy, which you would call solar wind. Plasma, fourth state of matter. Superheated gas, where atoms have lost some of their electrons. I told you they split out of their parent element, okay? And they create a mix of charged particles, ions and electrons. Where do you find plasma in daily life? You can see plasma in lightning bolts, electric sparks, glow sign inside neons. They all have plasma inside. Extremely charged particles because of heat, extreme heat. Okay, superheated. Now remember, Earth also has its own magnetic field. Okay, Earth has its own magnetic field, just like the sun has its own magnetic field. Sometimes what happens is certain particles from the sun, right? Really, remember, the sun has extremely charged particles. That's something unique. Okay, plasma, very charged particles, so they also have heat, they have light. Usually, when these particles, suppose they fall towards the Earth, most of the time the heat our Earth is able to absorb. Okay, and the particles, our own magnetic field, Earth has its own magnetic field, so it pushes these particles out, back into outer space. Earth doesn't receive them. But in certain conditions, what happens is this solar material, okay, it mixes with our own magnetic field. Instead of being pushed out, it comes inside the Earth. And that's when you see these kind of unique things happening, like in the northern, we call these the northern lights, right? You call it the aurora, lights in the sky. So North Pole Aurora Borealis, South Pole in Aurora Australis. How it happens? Charged particles from the sun get pulled in by Earth's magnetic field. These are only in very unique cases. Otherwise, usually the sun's particles are not received by the Earth. Our own magnetic field would push it out. And the heat is absorbed already by our atmosphere. So we don't get to see this in Guwahati. Okay, but I mean, like you won't get to see it. So you'll have to go to, that's why we'll go and see the northern lights. You've seen, a lot of these YouTubers would go and see. This is a very unique phenomenon where these solar particles get pulled in by the Earth rather than being pushed out. Only under certain conditions because of our own magnetic field. Magnetic fields can interact very differently. Okay, there are no rules for this. They interact very differently. And so if our own magnetic field attracts the particles from the sun, they pull it towards the Earth, then you will see something like this. Okay, so basically this is all your charged material. This is all your plasma that you'll see on the sky. Okay, emitting all the heat and the light. That's it. Sun, this is pretty easy. Was it fine for you guys? Nay? Just tell me, what did you not understand? Then we'll do a few MCQs from this. I'll ask you questions. So tell me, before I ask you questions, you ask me any part that you didn't understand. If I'm going to look at this.
And the flare.
The?
Flare.
The flare. Solar flare. It's like an explosion basically because of the magnetic disturbance. I told you, plasma logot ki thake? Magnetic field. Right? So magnetic field, imagine them to be like springs. So they remain in that constricted form most of the time. But in certain unique cases, ki hoy, his spring to release kori diu joti. Duta tinta spring joti ekelage release hoy. Some springs may break, some may get intertwined. Similarly, in the case of magnetic field, in certain cases, some amount of the magnetic field may intertwine together. Okay, and they exert an enormous force on the sun. Because of that, যেতিয়া magnetic disturbance হয় মানে ধৰা intertwine হৈ গ'ল বা magnetic field ভাঙি থাকিল, okay, then in that case it has an impact on the sun, and that force causes a certain amount of explosion to happen. So certain amount of material, solar material ulai pore. It's because of magnetic disturbance. Doesn't happen all the time, okay, but it happens in certain cases where magnetic disturbance হয়, or magnetic lines coincide or they join or they break. Because of magnetic disturbance, it causes an impact on the sun. Ujisa. You have to understand it that way. Just imagine, I told you best is to understand it as springs. Just imagine spring gita eneke ase. Eneke thakile thike ase. Gote gita jodi ma ekelage eri diu under some unique circumstances, ma eri dile ki hobo? Eta logot gulmal lagi jabo pare. And remember, it ebur ki hoy? Force hoy. Magnetic field is nothing but an invisible force. So imagine all the force coming together and it's happening in the surface of the sun. Won't it have an impact on the sun? So force to really both strong hoy, in unique cases, it may cause a certain amount of solar material to explode. And that explosion is what you call a solar flare. Flare mane English or flare matlab explosion hai. Like she flared up. Agar kisi ko gussa aata hai, we say, oh, they flared up. Flared up matlab explode ho gol. So flare, solar flare is like a solar explosion, which is caused due to disturbance in magnetic fields. Okay, heneke bujiba. Iman kini monot thakile hol, itman detailot nohumale hol, kinu basic hekini monot rakhiba. Magnetic disturbance hole flare hobo pare. Our flare hole ki hoy? Solar material, certain amount of it, not the entire sun obviously, but a certain portion of it may get erupted. When a solar flare happens in a larger scale, okay, suppose magnetic disturbance is very large and it's not just a flare but it's of a higher intensity. It's called, wait, I had it written it down, some ejection, yeah, it's called a coronal mass ejection. Coronal mass ejection, mass, you understand, matter, okay, and eject means it's thrown out, and it happens where? In the corona, in the outermost layer. Right? So that's why it's called coronal mass ejection. When the flare is of a bigger density, you can call it a coronal mass ejection. I'll write it down for you.
What is this prominence?
Which one? Okay, yeah, these are like rings of the plasma. Okay, the plasma can sometimes form ring-like structures. Okay, you can imagine it to be like a shoelace. And that's what you will call prominence, when these plasmas form these rings. Okay, and so usually what happens, if the best example is a shoe only to understand this. Okay, so your shoes, right, what happens is, can you pull the shoelace completely out from the hole? No, right? It actually prevents the shoelace from coming out completely. That's what happens when it's this prominence, these ring-like structures, the plasma rings, okay, when the electromagnetic field does not allow it to go in. Then it is this actually that eventually cools on the corona and forms your sunspots. You'll call it prominence, the rings that are formed by the plasma. Okay. What did I tell you? CME. It's a bigger flare. Okay, what is it? Coronal mass ejection. Coronal mass ejection. Okay, so when the flare happens on a larger scale, remember CME, coronal mass ejection. Due to what? Magnetic disturbance. And what causes the plasma to move from the core to the corona? Huh? Earth rotation? Solar rotation. Earth ka rotation, sun se it will not impact. Solar rotation and convection. Okay. What is faculae? What is, okay, tell me, what is faculae also called? Little torch. Okay. Where do you find the faculae? Specific, kahan pe? Yeah, correct. Sunspots. In the edge of the sunspots, you would find magnetic field where a certain amount of plasma is concentrated. Okay, which is why fusion is still happening. Energy is still being released in the form of light, and the light that is released there in the edge of sunspots is what you call faculae. Okay, so it sort of counter attacks the sunspots. So sunspots are making it dark, but the faculae again helps to regain the light. And the faculae, the light emitted by the faculae is more than enough for the sun to keep burning bright, okay, to be emitting light. Okay, I'll ask you a few questions. Are you ready for the questions? I'll ask you MCQs. Prepared a few. Okay, first question, very simple one. Primary source of energy for the sun. I'll give you options. Listen carefully, okay? Primary source of energy for the sun. Through which process does the sun get its energy? Nuclear fission, chemical reaction, nuclear fusion, or gravitational collapse? Nuclear fission, chemical reaction, nuclear fusion coming together, or gravitational collapse? What is the process through which the sun gets its primary fuel, its energy? Nuclear fusion. Okay. Next, which layer of the sun's atmosphere is visible during a total solar eclipse? This we didn't do here, but I'll give you the answer anyway. Okay, just try and guess which layer of the sun's atmosphere is visible during a total solar eclipse. Photosphere, chromosphere, corona, convective zone. Photosphere? No. Remember, when you're coming to what is your answer? Corona. Okay. Anybody else? You want to try? Photosphere and chromosphere. What do you think? Chromosphere. Okay, chromosphere. Anybody else? Options are photosphere, chromosphere, corona, and convection zone. Okay, the right answer is the one that she gave, corona. Corona becomes completely visible during a solar eclipse. What is the sun mostly composed of? Oxygen and carbon, this is so easy. Hydrogen and helium, nitrogen, oxygen, iron and nickel. Hydrogen and helium. You can sleep and write this answer also. Which process generates the magnetic fields of the sun? Which process generates the magnetic fields of the sun? Gravitational collapse, solar wind, solar dynamo, and magnetic reconnection. This is actually too in detail, not so appropriate for you guys. But the correct answer for this is solar dynamo. Just write it down. Solar dynamo. The process is called solar dynamo, through which the sun generates its magnetic field. Okay, basically the particles are charged and split. Okay, the electron is separated. The process is called solar dynamo. Which part of the sun's atmosphere is the hottest layer? Listen to this, okay? Don't, when you say, if I give you this question, which part of the sun's atmosphere is the hottest layer? Options are corona, photosphere, chromosphere, core. What is it? Which part of the sun's atmosphere is the hottest layer? Okay, if I'm going to give you a trick question like this and I put core, don't just say, oh, hottest sun, core. No, I'm talking about the atmospheric layer of the sun. Corona is not a part of the sun's atmosphere. Okay, when you talk about the atmospheric layer, it's the outermost layer of the atmosphere of the sun that's the hottest, which is corona. Correct answer is corona. What causes the sun to emit light and heat? Options: nuclear fission, chemical reaction, fusion, gravitational collapse. What causes the sun to emit light and heat? Fission, fusion, chemical reaction, gravitational collapse. Fusion. Okay, just remember, light, heat, fusion. Okay, it has to be that. Which layer of the sun is most visible from the earth? Options are chromosphere, corona, convective zone, and photosphere. Which is the most visible? What is the one that we see? Corona we see only during solar eclipse, remember that. I don't see it. What is it? Chromosphere? No. Yeah, photosphere, okay. Just remember this, the layer that we can see of the sun is photosphere. Most visible to us. What is the approximate temperature of the sun's core? Options: 5,500 degrees Celsius, 15 million degrees Celsius, 6,000 degrees Celsius, 10,000 degrees Celsius. Million wala. Okay, correct. The core is at 15 million degree Celsius. And what is the temperature of the core? Huh? Yeah. Okay, 16 million. Here, I mean, in some they've given 15, some they've given 16. Okay, 16 million, 15 million, around that. Okay. And what is the temperature of the corona? 6,000 degrees Celsius. Okay, roughly. So interestingly, when you're talking about the atmosphere of the sun, the furthest layer is the hottest. Okay, why? There are only guesses and assumptions for this even now. So there's no clarity, so I've not mentioned here. There are a few hypotheses you can check out online. There are about 4 to 5 reasons, but they're all guesswork. And it's never come for your NDA and all, so not so important. But remember, the innermost layer of the sun, the core, and the outermost layer of the sun's atmosphere are the hottest. So it's the core and corona. Core and corona. Okay, just go through and tell me if there's anything else. I think it shouldn't be that difficult. And how did the sun also start? What was the primary structure? What was the primary structure?
Yes.
Gas and? Okay. What is it called? Huh? No. The basic word which we use all the time. Yeah. Okay, nebula. Remember, the sun is a star. We studied about the evolution of stars. So the base is the same for all. Okay, but here we've just done a little more in details. Should I ask you a little about the evolution of stars? Do you all remember? Pucho. So, okay, just tell me, what was the first stage? Okay, it starts with your nebula again. Uske baad? Protostar. Okay, that's like the infant stage, not even the infant stage, the fetal stage, okay? And as it grows after that, what's the next stage? The intermediary stage. T-Tauri stage. T-Tauri is called, it's like the teenage phase of a star, adolescence. Then it grows up to be a fully grown, functioning adult. What is that? Huh? I heard somebody say it. What was it? Correct. Okay, main sequence, that's the adult phase of a star. Then gradually over time it begins to lose its hydrogen fuel, right? It's aging, the star is aging. So it's going to the next stage. What is it?
Giant.
Correct, okay. Red giant. And if it's really big, what do you call it? If the star is really big, it's a super red giant. Simple, just add super, okay? Super red giant. After that, what's the next phase? White dwarf, okay? And will it all remain as white dwarf? Will all stars remain as white dwarf? नहीं. तो क्या होता है? Some stars remain as white dwarf, and some, what happens? Supernova explosion होता है. क्यों होता है?
More than solar mass.
हाँ, correct. हाँ. Okay, when the mass of a particular star is 1.44 times more than solar mass, then it'll explode, right? And the explosion causes it to either remain as a दो चीज़ें हो सकता है. हाँ, एक अगर छोटा स्टार बन जाता है, it remains as a neutron, otherwise black hole. Okay, and then again after that explosion, that same material, it goes back to the stellar cycle, and then again that same dust, the same gas, over time again it'll come together, फिर से accretion होगा, and then again the whole structure will be formed again over time. So it's like a recycling process that keeps happening. Okay, let me think what other questions are there. Okay, sun's stars color. What do you remember about the color of stars? What does it depend on? Huh? Very good. Surface temperature. So what do you remember? Tell me.
The hottest.
Very good. Blue is when it's at the hottest surface temperature. Then
White.
white is when it's white is I just told you, remember the flame. So the hottest part of a flame is always blue. The next layer is white. That's when it's medium. The surface heat, the temperature is medium. And when it's cooler, it is what?
Red.
Reddish. Okay, so that's what the color of a star is dependent on that. on the surface temperature. So if it's really hot, it's really active, it's going to be bluish. If it's going to be medium, white, and if it's on a cooler side, okay, it's aging, the star. So temperature is also reducing, fusion is less, so it's going to look reddish, okay. Okay, fine, let's wrap up with that for today. I will send you some multiple choice in the group. You can go through it. What is the full form of CME? Coronal? Yeah, coronal mass ejection. Okay, chalo. I hope you all understood. All okay? Okay, you can always ask me questions on Friday. I'll meet you all on Friday. Huh? Thank you.